And today we are talking about forces. We had already talked about forces a little bit. In fact, we've actually, in your lives, we've talked about forces a lot. I want you to write down the objective, which it has come to my attention. I mean, I have drawn it to my own attention that I have been forgetting to write down the objective in several of these this year, so I'm trying to do a better job. The objective is analyze and interpret data involving forces and their effect on motion. Analyze and interpret data. Interpret data. I think I spelled interpret with too many E's. Interpret data regarding, is that the next thing? Involving. Ooh, that's cute. Involving, I wrote this, so it's okay for me to say that. Involving forces and their effects, maybe? Forces and their singular effect. They do have one effect. I have to write that really small. On motion. So just as I have written that down, I mean, to me it makes sense that if I had to go to the trouble to write that down, that you should too. So you should write that down. You also might head this section of your notes forces, because that's what we're talking about there. Talking about today. That's a great way to start this. Yeah. I'm so glad you're here today, Allison. Thank you for starting the video in that way. You already know what that arrow means. You've been here enough. Even you have probably paid attention enough to know what the arrow means, right? What are we going to do first, Trey? And why don't you just do it? Yeah, okay. I hope you did do that. What's this arrow mean? I drug this thing down. What are we going to do here? No, drug, as in the past tense of drag. Go on. Yes, tell me it. No, you don't need to look in your notes. Just tell me. What's a force? Okay, it can cause movement. Let's put a different arrow over here. This is the other arrow. Can, and I want you to be very specific with that word. Can cause movement. There you go. The definition I was looking for, I thought you'd get, is a push or pull. That's very basic. Give me an example now. I bet this is Friday. I bet you could give me an example of a push or a pull. Give me an example from your night last night. Give me an example. I want to hear a story about a push or a pull that you had from last night.
Push the ball over the ball.
Yeah, okay. That's some unnamed person. You did what? Just like on the for volleyball. I thought you meant like you were getting to the concession stand. Okay, let's use that one. That's the one I was actually kind of looking for. I'm glad you all have examples, because that's what a discussion is. We're discussing the examples of push and pull. And let me tell you, even if you think that you were getting away with telling stories for 10 seconds that were not about this, everything involves forces. Everything in your life involves forces. If you were talking about chewing at Domino's, I don't know if you went to Domino's. I was at Subway, and I know you guys weren't there because I was there. If you were chewing, that's a force. If you were, all I can think of are inappropriate things. If you were smacking your brother's butt because he did a good job at football, that's a force. If no, everyone's embarrassed. That's like that's the lightest level of inappropriate humor. I didn't think it was that bad, but now I'm gonna have to cut it. If your mom hit a dog with the car on the way home, let's draw all of those. Let's not draw the second one. So we got a football helmet. This is how you draw a football helmet, and a guy wearing a football helmet. Okay, you got a football player, and you got another football player. This is how I understand football. I don't even know. And this one, yeah, that's a good word. This one has an eagle on it, and this one has a ram on it. Oof. I don't care. That's a ram. It's just his little head. No, it's the ram horn. You know how the helmets have horns on the side of them? This object, now listen, here, this is where we are talking about science, and you might have forgotten, and you would have been excused for forgetting, but we are talking about science. if this object, I guess is probably a good word for it, puts a force on this object, does this object necessarily move? Be very careful. Not always, okay? Thank you. Since it's a hawk, it's gonna, yeah, good. Because of go team. Yes, Chloe, you're really on it today. That's right. Okay, so because of inertia, inertia, please remember the word inertia from last year. You should have had this, an I. You should have had this word defined. You should have had this word defined in your vocab. You definitely had it defined last year, although, again, you would be excused for forgetting all of last year. Inertia is an object's resistance to a change in motion. And it's extremely important that you are able to collapse this phrase, change in motion. What is another word for, what is one word for change in motion? No. Change in motion. Motion itself is movement. Thank you, Avery. Remind yourself from the last lesson, that does seem like a lifetime ago, that a change in motion is acceleration. So inertia is an object's resistance to that. But just as Trey said earlier, forces can cause, I'm going to put in parentheses here because he didn't say this, but I'm going to add it, change in movement. Forces can cause a change in movement. Do you see that we have now three kind of concepts? We have forces, we have inertia, and we have acceleration. Do you see how they're related? Well, forces can cause acceleration, but that thing which resists that acceleration is called inertia. So, meaning every time if I push on this chair, I don't know what you call this, end table. I'm using it as an end table. Stool. Will it always move? If I put a force on this, must it move? No. If I'm trying to think of the name of a football player. Isaiah, do you play football? If Isaiah puts a force on, give me the name of a Hay Springs boy. Just first name. This is Trip. So if Isaiah puts a force on Trip, must he move? No, he doesn't have to because, one, because of inertia, and two, there's another thing going on here. What do we call another force? What do we call another? There we go. So let's analyze just right now. Let's analyze the forces on Trip. So we have Isaiah. Let's start over. Give me one force acting on Trip. There we go. The force of gravity must act down. F sub g. Write this down, please. F sub g is the force of gravity. Why? That's really actually come to find out, very scientifically tricky answer. Why does gravity exist? But at your level, gravity exists because all massive objects attract all other massive objects. All massive objects. You would think the word massive, as in massive pit bull or massive woman, means great big, but in science, massive just means it has mass. All massive objects attract all, and that means all, other massive objects. Where? Where does this occur? All massive objects attract all other massive objects. Where? In the universe. That's exactly right. Everywhere. So it's technically true that the force of your gravity affects the planet Neptune and vice versa. So to some extent, you could make a scientific case for the horoscope, that the stars affect your life. Although, probably not really, as we're about to see, because forces can be balanced, and they do diminish over distance. And I'll show you that equation right here. The equation for this concept is F sub g equals capital G times the quantity m1, m2 over r squared. We're going to go through this in a second, but first write it down. I'm going to take a little drink of my mystery fluid, and you write that down. Write all this down. It's called an equation. It's a way that we do math.
No, a little sign with a G.
This means that all of this is this equation. Okay, we're going to talk about it. Okay, so we have F sub G, I'm going to put in parentheses here, W, is what? What is the force of gravity sometimes called? It starts with a W. The force of gravity acting on an object is called its weight. And I know nothing about Tripp, but just because I want to be mean to Haysprings, what's the force of gravity acting on Tripp, would you say? It's all muscle. 600 pounds of muscle. He's a steak. No bones even. He's just 600 pounds of hamburger sitting in the middle of the field with a Haysprings Hawks helmet on it. The weight of an object, we'll talk about in a second what it's measured in, but we're going to have a unit there, which I'm running out of room, but I hope you have room for that. So the weight of an object is the product of, what's the word product mean? Yeah, multiplication. The product of capital G, the universal gravitational, I'm going to have to abbreviate that, constant. And this quantity not only has a unit, which we'll talk about in a second, but it also has a known value for our universe. That sense almost implies that there must be other universes we don't know. All we can have experience with is our own universe. Scientifically, the only things we can observe are within our own universe. And so in this universe, this quantity is always, when we measure it, 6.67 times 10 to the negative 11th. I'm sorry I ran out of room. Newton times meter squared over kilogram squared. That's the unit for it. Negative 11th. I know it's getting tiny and it's getting in a corner, and I've really backed myself in this corner, and I'm going to start biting you guys like cornered animals do. I am actually getting frustrated, so if you get me further in this corner, I'm going to start biting. 6.67. Are you listening and reading and trying to read? Are you serious? You of all people. 6.67 times 10 to the negative 11th, and the unit is Newton times, this little dot, we use this dot for multiplication, meters squared over kilogram squared. M1 and M2, can you guess? Mass of objects. What do we measure mass in the SI? Well, then don't say anything. What do you measure mass in the SI? Someone who does know. Kilogram. Good. And then R, we sometimes also use D, or D, is what? Can you guess what might lowercase d be? Distance. It's the distance between them. It's actually, I'm going to specify the distance between their centers of mass. In physics, a lot of times we pretend like an object is all concentrated at its central point. So that's why I've drawn this dot here on Tripp. That's presumably all of his mass is centered in his head, in his meaty skull. Same thing with Isaiah, except slightly less meaty, presumably. But we pretend in real life, your mass is probably not centered in your skull. It's somewhere around your belly button. But where we pretend like you can be reduced to a point where all of your mass acts as a point source. And that's really important because look what happens in this equation if we have no distance between objects. If this were 0, we can't divide by 0 though, can we? In fact, if we did, in this specific equation, it would actually be a black hole because there would be no distance. Any kind of mass with no distance would be dividing by 0, which would be a black hole, and you don't really want that. And so that is to say that even though I feel like I'm touching the board, actually the center of mass of my hand and the center of mass of the board are separated by the stuff around them, right? So things are never actually, their centers of mass are never in contact. I ran into that. What do we measure distance in the SI? Yep, meters. We measure distance in the SI in meters. So now, if we take this equation, this unit, Newton times meter squared, divided by kilogram squared, and we multiply that by kilogram times kilogram, and we divide it by meters squared, what unit do we end up with from this one? If we take this big thing, Newton times meter squared, maybe I'll do this over here for you, and then I'm going to erase it right away. Newton times meter squared per kilogram squared. Oops, kilogram squared. And we multiply. See how R is squared?
Yes.
Good. We multiply, actually that would be dividing, so 1 over the meter squared. And then we also multiply it by a kilogram, right, because we measure mass in kilograms, and we multiply it by another kilogram. What do we end up with from all this, looking at it algebraically?
Too much.
No, it's just Newton. So what do we measure forces in then? What do we measure weight? Newton. And it's important that you know that, or D. It's important that you know that this acts for any two objects. So do you have a mass? Does Trip have a mass? Yeah, 600 pounds. That actually mass is measured in kilograms. Pounds are a weight unit. That's an English unit, but pounds are actually a weight unit, which is different from a mass unit, so we'd have to find it in kilograms. But anyway, you could, right now, I don't know how far apart you guys are. How far is Hay Springs from here? Like 50 miles-ish? Yeah. I mean, whatever that is in kilometers. I had it written on the board yesterday, but so roughly 80 kilometers. We could put 80,000 meters here and square it. We could put your mass here. We could put Trip's mass here. We could multiply it by this, by the way, big number or small number, looking at the universal gravitational constant. Small. Very, 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 very small. If we were to write it out without scientific notation, it's 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 6, 6, 7. This would be the universal gravitational constant with this unit. So we could multiply your mass. You're all very small. Most of you are all very small. And so we'll say maybe 50 to 60 kilograms. So if we took, just in our heads, some very basic math. If we took 50, even if Trip's mass were 600 kilograms, which I'll tell you it probably isn't, that's a lot of hamburger, 50 times 600 is what? What's 50 times 600? You guys aren't good at this. 50 times 600 is yeah, it's about, you are good at this. It's about 3,000. And then we divided it by 80 squared, right, which is 6,400. We've already got about 0.5 here. And then we multiply it by this tiny, tiny number. We get a force, the force of gravity acting between you and this man who has become the star of our presentation without even realizing it. We would have about half of that. So the force of gravity acting between you and this hypothetical man from Hay Springs would be about that. He's not hypothetical. He's very real, Ada wants us all to know. There should be another zero in there. Okay, it would be this many newtons. This is your weight in the field of gravity of Trip from Hay Springs. Also, though, it is also Trip from Hay Springs' weight in the field of gravity of your body. And this is a very, 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 very small number. The weight of a paperclip, a little baby paperclip, is about, somewhere a little bit less than 1 Newton. And so the weight of a paperclip in Earth's gravity is about, we'll put here, about 1, maybe 0.5. And that's about 1 billion times greater than the force of gravity between you and this other person. And so does this exist? Technically. But the force of gravity between objects is so small unless, why is the paperclips so big here? What's the other object? Without, I think I might have said it, but what is the other object implied? Earth, right? And that, having M1 be Earth's mass, which is on the order of 10 to the 25th, makes it so the whole thing ends up with like fairly large numbers for this. So this is how gravity works. Back to our force diagram, we have one force acting on Trip here, the force of gravity, right? What other forces are acting on this object? The normal force. Thank you for remembering that. And unless he is right now falling like through the football field, it should be what? How should it compare to the force of gravity? It should be equal. So we have the force of the normal force. We have gravity always acts down in Earth's, that's how we define down, the direction that Earth is. Does the normal force always act up? No. This is perpendicular to whatever surface. That's how we define the normal force. So if the football field is mostly flat, which I would guess that it is, right? I wasn't there. Not at Hay Springs. It's actually on a hill. It's on the side of a mountain. They just bamboozle you to run uphill. So it's perpendicular to the surface. We're going to pretend it's flat. So this does counteract gravity. And then we have this push force, probably actually greater than the weight of this object from this direction. So I'm going to put F sub P for the push force. But let's pretend he's not moving right now. What other force must be acting this way? We got a mystery force here that's acting against the push force. It's not just his inertia. In fact, inertia is not a force, so it's not that. What's holding him back? Like if I were to go and push Ada,
Friction.
there you go, friction. Friction. You're not wrong though, actually, because you just said him, and I thought you were talking about the inertia, like his weight is resisting, but actually he probably is pushing too. So let's put a little bit of that. So he's pushing back, obviously not as hard. Isaiah's the better football player. But there's also a little bit of F sub lowercase f, which is the force of friction. And the force of friction is another important thing in our discussion. Force of friction resists motion. Only when the objects are doing what? In contact. Only when the objects are in contact. Now, when an object moves, how much does it move? How much does it change its motion is given by this equation. Let's say that we did have, when we add all these things together, by the way, what do we call that? Do you remember? The sum of the forces, that's this is the capital, yes, thank you. This is the capital Greek letter sigma, which just means sum of. So the sum of the forces is we call the net force. We add all these things up, and that gives us the net force. If F sub net equals 0, what do we call that? If they all add up to 0, we call that a balanced force. I'm glad this is supposed to be reviewed, and it is, and I'm really proud of you for that. If F sub the Nate force, if F sub net is not equal to 0, we call that then unbalanced. And what must unbalanced forces always cause? Well, guess what, baby? We are right back to the beginning. Unbalanced forces always cause acceleration, which is a change in motion. So unbalanced forces cause acceleration, and here's the equation for that. This will be your worksheet, and this is where we'll end because after this point, you'll learn the rest of the worksheet. So F sub net equals the mass of an object times its acceleration. We would, in handwriting, we would put lines over these because they are what kind of quantities? Do you remember? Vector. They have magnitude and direction.
Oh, yeah.
This is easy math. We didn't do this last year. The 8th graders this year are doing it. We should have just done it. This is so easy math, though. You shove in, right, here's the equation. If we were going to do it, we then substitute F sub net now equals, let's say, 10 kilograms times 2 meters per second squared. What does F sub net equal? The solution? 10 times 2 is 20. Kilogram times meter per second squared, I'll give you a hint. Well, the answer is kilogram times meter over second squared, which is the same thing as 20 newtons. This kilogram times meter per second squared is a newton. Remember how we talked about derived units? The newton is a derived unit. A newton is a kilogram times a meter per second squared. Your book does talk about momentum, and in fact, you should know that the way Newton himself, you remember Newton's laws, right? Because that is on the test, and I'm just assuming that you remember Newton's laws. So if you don't, brush up on Newton's laws. But Newton himself, when he described these, described a force as a change in momentum. Momentum is equal to mass times velocity. Those should all have, this is the letter P. At the beginning of the year, we used rho. Remember rho? This is not rho. This is just P. Momentum is mass times velocity. Do you see the relationship between momentum, which is mass times velocity, and force, which is mass times acceleration? What's the relationship? Well, it's the same as the relationship between velocity and acceleration, right? It's just that this one, velocity is describing an object's motion, and acceleration is describing an object's change in motion, right? So does it make sense for Newton to describe force as a change in momentum? Let me give you the analogy. Acceleration is a change in velocity, and so force is a change in momentum. Does that kind of make sense?
Yeah.
Do you think you could do this math?
Yeah.
Would this be hard math or easy math for you? Easy, because the worst thing you're going to have to do, the hardest thing mathematically you're going to have to do with this is manipulate it, but you can do that, right? It's all in one line. Just like our moms. Ah!